So the next lecture will be given by Professor Clark from UIUC, who will be talking about many-body localization in the language of tensor networks. Let's go.
Great, thank you very much, and thanks for inviting me. So what I'd like to do in the next two lectures is to talk about many-body localization, and particularly for at least all of this lecture, maybe most of next lecture, to talk about it sort of in the language of tensor networks. So there are going to be sort of two broad aspects of that. One is that we're going to find that the language of tensor networks gives us sort of a conceptual understanding of many-body localization. And then secondly, what we're going to find is that we're going to find that tensor networks allows us to develop algorithms that will let us compute properties of many-body localization and understand it better. But we'll start by trying to understand sort of the many-body localized phase, and we'll try to understand it in the language of tensor networks, so sort of a conceptual language. I'm going to be writing on the board, so if people want to come down and have trouble seeing what I'm writing, that's a not unreasonable thing to do. Okay, so that's the game, and so we're going to learn both about many-body localization, and we're going to go ahead and we're going to learn sort of what we need about matrix product states and tensor networks. So I'll assume that you know nothing at all about matrix product states and tensor networks. If you know some things, that's great, but I'll go over the things that need to be known. So what I'm going to do actually is I'm going to start largely kind of with an outline, but also in some sense with a result. I'm going to start with kind of the three things that we'd like to understand in the next lecture and a half. And then what we're going to do is we're going to spend the rest of the time essentially unpacking those three things. So the first thing I'd like to tell you is I would like to tell you about excitations. And understanding many-body localization is really a eigenstate phase transition. And so it makes sense that if we're going to understand many-body localization, we should start by understanding excitations. So let me first give you kind of a stupid kind of pathological example that will inspire the sense in which we want to understand excitations. So let's imagine that we have a Hamiltonian. For these lectures, I'll be talking about spin Hamiltonians, but one can, of course, talk about either spin or electronic Hamiltonians. It's in one dimension. And let's start with something sort of pathologically boring. Let's say I have a completely non-interacting system. So I just have some magnetic field that's sampled from some disordered potential from minus W to W. And then I have a sigma IZ term. Okay, so this is not a many-body localized phase. In fact, it's a very boring thing, right? It's just a non-interacting system. But we know lots about this non-interacting system. So for a given disordered realization, I have some magnetic field. That magnetic field has a different strength at each site. And then you can ask yourself, what is the ground state? And we all know, obviously, what the ground state of this is. We have a bunch of spin a half, and they're pointing in the direction opposite the magnetic field. And then you can say, look, I'd like to understand what the excitations of this system is. And the excitations of this system are obviously trivial. I take some number of these spins. These spins are a product state. In fact, they're even a boring product state. They're either sort of spin up or spin down. And I flip some finite density of these spins, some finite fraction of these spins. Maybe I'll flip those three. And that gives us a finite energy density excitation. Okay, so as I said, this is a non-interacting example. It's reasonably simple. Nonetheless, this sort of inspires us for the kind of result that we'd like to have, not for a non-interacting system, but for an interacting many-body localized phase. So we'd like to be able, in the same spirit, to say, look, the ground state looks like something simple, and then what I'm going to do is I'm going to kind of flip some of the ground state spins, and that will give me all of the finite energy density excitations. Okay, so that's kind of going to be our guide star, sort of our goal, and what I'm about to tell you is I'm going to tell you that actually we can accomplish something like that. And then, as I said, we'll unpack that statement. So I should make a point here. So everything in today's lecture, we'll be talking about phases that are typically go by the term fully many-body localized. So this means that there's some Hamiltonian, and that Hamiltonian is many-body localized at all energy densities. So at the moment, we're going to preclude situations where we have a mobility edge, where some energy densities for a given disorder strength are localized and some are delocalized. Okay, so now, instead of having our non-interacting system, let's add some interactions. Let's add a Heisenberg term, sum over ij, sigma I, sigma j. So now we have actual Hamiltonian with some interactions. And now we want to ask ourselves, can we go ahead and can we have a description of the ground state and the excited state in a compact and sort of pretty way like that? So this is what many people call kind of the standard model of many-body localized spaces. This has been studied a lot. It's known that W around 4-ish and larger, it's many-body localized, and on the other side is still ergodic. And so our question now is over here, in the many-body localized phase, can we describe the eigenstate simply? What else can we know? Okay, good. So now I'm going to tell you, I'm going to sort of outline what we're going to spend the next lecture and a half understanding. So my claim is the following. So I'm going to make three, what it turns out to be interrelated claims. So the first claim is going to be about these excitations. So the claim is that the entire spectrum, all excitations of the many-body localized phase can be described in the following way. Can be described, well, first it's going to be, they're all going to be by matrix product states. Matrix product states is a one-dimensional tensor network. It's the thing that DMRG spits out when you run it. If you don't know what matrix product state is, that's okay. I'll tell you in detail in a moment. But they can all be described by matrix product states. And in fact, what is much more powerful is not only can they all be described by matrix product states, but a ground state typically is described by 2n matrices. So with 2n matrices, you can get a typical one-dimensional gapped ground state. And my claim is that the entire spectrum is going to be described by 4n matrices. And then it's going to be described, morally speaking, in exactly this way. The ground state, there's going to be, here we have a spin for each site. The ground state is going to be not a spin for each site, but a pair of matrices for each site. Again, we'll outline this in detail in 2 minutes. But the ground state is going to be a pair of matrices for each site. And if we want to get one of the finite energy density excitations of the many-body localized phase, what we're going to do is we're going to pick some sites, and we're going to change the matrix on that site to something else. So maybe we'll pick sites 2, 3, and 4, and we'll change the matrix on site 2, 3, and 4 to some other matrix. And that other matrix will be, just like here we took spin downs and flipped them to spin ups. That other matrix will always be the same. If I'm going to change site 2, I'll change it from sort of the matrices G2 to the matrices E2. This will produce a new matrix product state, G1, E2, E3, E4, dot, dot, dot. And that will be one of the excitations. Okay, so that is claim 1. We will unpack what a matrix product state is, what I mean by those things, et cetera, in 2 minutes. But let me just start with sort of this initial claim. So that is, sorry. That is one of the things that we will see in the next 2 lectures. The second thing we'll see, which turns out to be equivalent, is that there is a short matrix product operator. I'll tell you what that is in a minute, but you can morally just think of it as a quantum circuit. There's a short quantum circuit that diagonalizes the MBL Hamiltonian. So you have some MBL Hamiltonian, and you say to yourself, look, I would like to write this MBL Hamiltonian not in the current basis, but in diagonal form. To do that, I'm going to use some quantum circuit, some unitary operator to do that transformation. And then one can ask about the depth of that unitary operator, the depth of that quantum circuit. And it turns out that there is, in the many-body localized phase, short circuits, a single short circuit that diagonalizes the entire Hamiltonian. So it turns out that these statements imply each other, that if this is true, then this sort of beautiful structure of the eigenstates exists, and vice versa.
When you say short, is that with regards to the dimension of the system?
When I mean short, that is with regards to the size of the system. So really, what I mean is that, what I mean is as the system size, so I'm going to talk only about one dimension, and as the system size gets bigger and bigger, the circuit depth will not get any longer. Now, I will, in 10 minutes, qualify that because we're talking about a disordered average system, and so I really need to be a little bit more concrete about what I mean with respect to that disorder average. But up to those details, which we'll see in about 10 minutes, what I mean is that the depth of the circuit won't get any bigger if you have 100 sites, 1,000 sites, 1,000,000 sites. Great. By all means, continue asking questions while I go through. Certainly that will be a more efficient approach than asking questions at the end. Okay, good. And then I will make sort of a third claim. And the third claim is in the MBL phase, there are n Hermitian operators. And these n Hermitian operators have the property that they all commute with the Hamiltonian, that they all commute with each other, that they are orthogonal, etc. Yes?
Can you generally write a little bit larger?
Yes, I can try to generally write a little bit larger. Sorry. Okay, good. So claim 1, claim 2 is this, claim 3 is that there are a bunch of Hermitian operators. These are essentially conserved quantum numbers. Yes?
These ni are they related to the system size or?
There are, yes, the system size is of length n, and there are n of them.
So it's like an integral system.
It is like an integral system. In fact, one good way of thinking about many-body localized spaces is to think about them as a system that is emergently integrable. Typically, when you have your favorite integrable system, you fine-tune to a very special point, and at that very special point, the system is integrable. Here, we have a situation where we have an entire phase, and that entire phase is essentially integrable in the same way. So here, there's an emergent integrability. And it's exactly for this. You have a bunch of commuting, local, quasi-local Hermitian operators. These are essentially quantum numbers of the system. These are all two-state quantum numbers. So if I want to specify an eigenstate, what I should do is for each one of these quantum numbers, for each one of these Hermitian operators, I should just specify whether my eigenstate is sort of up or down, 1 or minus 1, with respect to each Hermitian operator. And if I specify that, that specifies one of the 2 to the n excited states. Just like, and this is how integrability works, this is why free fermions are integrable, et cetera, et cetera. Okay, and so this is really a statement. These things are typically called L bits, but this is really a statement that there's a bunch of conserved local quantum numbers in the system. Yes?
Say if you have an Hamiltonian which is n by n, and if I consider all those operators that you are writing as ni as n times the projection operators, meaning one outer product without one, then I will trivially have n operators which commute with the Hamiltonian and commute with each other. And that I can do for any Hamiltonian.
Okay, good. So the Hilbert space is of size 2 to the n. But it is true, actually, that for any Hamiltonian, one can write such quantum numbers. But what is not true generically is that these Hermitian operators will be local. And that's sort of an important distinction.
Local in which space?
Real space. That there will be a spatial locality. That if one looks at the Hermitian operators, they will be sort of peaked at some site, and they will decay exponentially away from that site.
So the only qualifier for this quantum number operators to be local. That's it.
I'm sorry?
So the only these operators that are commuting with the Hamiltonian, the only qualifier that they have to satisfy is that they are local. That's it. Right?
They're local, they're orthogonal, they commute with each other. But yes, the special thing is that they are essentially quasi-local. Yes, Sanjay.
So how do these operate in the non-interacting case? I can define a set of them in the non-interacting case.
Yeah, so in the non-interacting case, say free fermions, you can define such a set. And so, morally speaking, this is very much like free fermions. It's just that we're able to do this generically in sort of an interacting system.
Does it help you to start with the non-interacting case and find these operators, or how is that?
Yeah, in fact, we'll see that these operators, I mean, here we're in a spin system, and you might imagine in the non-interacting case, these operators really are just the sigma IZs. And we'll see in the interacting system that they are just U sigma IZ U dagger, which is the rotation of them into the many-body basis.
So there's nothing that differs in the interacting case about these operators in the non-interacting case, I mean, fundamentally.
There is nothing very fundamentally deep that differs. I mean, there is a sense in which many-body localization is just adiabatically connected to the non-interacting case, in the same way that you might say a Fermi liquid is connected to a Fermi gas. It's true that a Fermi liquid is more complicated in a lot of ways than a Fermi gas, but in a very fundamental way, it's not sort of deeply different. And the same is true of many-body localization. Yes?
Just a comment on the Hamiltonian nonlinear phase will have a huge number of interaction terms in these elements.
Yeah, these things will look complicated once you do the rotation, although it's true that they're adiabatically connected to the simple non-interacting case. Yes?
So, sorry I already mentioned this, but are you taking the existence of these local operators as the definition of MBL?
So, no, what I'm saying is that, so, good question. So what I'm saying is all three of these claims are true, and any one of them implies all the others. So, in some sense, you can call MBL something where any of these things are true, and then the other things that I've written on the board follow from it.
What was the first?
So, sorry. Yep, the first thing is that the eigenstates are written in sort of this compact matrix product state form.
Okay.
The second thing is that there is a short quantum circuit that diagonalizes your Hamiltonian. And the third thing is that there are these quantum numbers that are local and conserved, etc.
Okay. So how does this compare to MBL as David Hughes was talking about it, like a lack of thermalization?
So, for example, we will see that this structure implies a lack of thermalization.
Okay.
So, as David Hughes was talking about it, he said essentially this is the phenomenology, this is sort of the properties of MBL. We're just sort of doing it backwards. We're saying, look, imagine one of these things are true, and then all these other things also become true, and then in addition, we can understand much of the observable phenomenology, lack of thermalization, immersion integrability, et cetera, that comes.
Yeah. And how often can you go the other way? Do you have a system that doesn't thermalize? You know that these.
Okay, that's a good question. That is not obvious, and in fact, as I said a bit earlier, here we're looking at a particular case where there's no mobility edge, but we know there are cases with mobility edges, and there some of these things aren't true, but nonetheless there is an energy density at which you don't thermalize. And so the other direction is not obvious and probably not generically true. But this is a good way to understand sort of the fully MBL phase, and then the phenomenology of that will come from this.
For the n permutation operators that you're considering,
Yes.
so is it a requirement that it commutes with each other, or is it just a condition that we are imposing?
It is a requirement for it to imply these other things, and it will be true as implication of these things. So essentially it's a requirement.
Okay, but if it even if it does not, like, we can change the Poisson bracket or the structure to a graph bracket structure to take care of the second class constraints.
I agree there are lots of things you could do, and maybe some of those things are still true of the MBL phase, and maybe some of those things imply these other things. But let's say this is the one we'll work with, and it is not clear to me that